In September 2023, the James Webb Space Telescope detected carbon dioxide and methane simultaneously in the atmosphere of a planet called K2-18b, and scientists could not immediately rule out biology as the source. That single measurement, taken 124 light-years from Earth, is the closest we have ever come to a credible chemical fingerprint that life might leave on another world. This is not a headline built on speculation. The data is peer-reviewed, published in the astrophysical journal Letters, and the team behind it, led by astronomers at Cambridge University, described their findings with measured language precisely because they understood the weight of what they were saying. They were not claiming discovery of life. They were saying something far more interesting. They could not yet rule it out. And when the James Webb Space Telescope is the instrument doing the looking, that distinction matters enormously. To understand why this telescope is rewriting the search for life, you have to understand what came before it. For decades, astronomers could detect planets around other stars, but could not see into their atmospheres. The technique used most often, called the transit method, works by watching a star dim slightly as a planet passes in front of it. That dimming tells you the planet exists, gives you its size, and with follow-up data, you can estimate its mass. What it cannot tell you, at least not with older telescopes, is what that planet's air is made of. That was the hard wall astronomy kept running into. You could find the address, but could not look through the window. Webb changed that. When a planet transits its star, a small fraction of the starlight filters through the planet's atmosphere before reaching the telescope. Different molecules absorb different wavelengths of that light. Webb, operating in the infrared spectrum, wavelengths invisible to human eyes, is sensitive enough to decode those absorption patterns and identify specific molecules. This technique is called transmission spectroscopy, and Webb does it better than any instrument ever built, by a significant margin. The telescope's primary mirror spans 6.5 meters, giving it roughly 7 times the light collecting area of the Hubble Space Telescope. That difference is not cosmetic. It determines whether you can read a faint chemical signal or miss it entirely. K2-18b is the planet that demonstrated this capability most dramatically. It orbits a cool red dwarf star, a type called an M-dwarf, and sits within what astronomers call the habitable zone. That term means the range of distances from a star where liquid water could theoretically exist on a planet's surface given enough atmospheric pressure. K2-18b is about 2.6 times the radius of Earth and roughly 8.6 times its mass, which places it in a category called a subneptune, or, depending on its interior composition, possibly a Hycean world. Hycean, from the words hydrogen and ocean, describes a theoretical class of planet with a hydrogen-rich atmosphere sitting above a vast liquid water ocean. The Cambridge team proposed this category partly to explain what Webb might find at K2-18b, and what Webb found gave that proposal new traction. The confirmed detections at K2-18b include carbon dioxide, methane, and dimethyl sulfide. Carbon dioxide and methane together are already notable because in many chemical environments they react with each other and break down. Finding both simultaneously can indicate that something is continuously replenishing them. Dimethyl sulfide is where the conversation gets genuinely consequential. On Earth, dimethyl sulfide is produced almost exclusively by marine phytoplankton, microscopic ocean life. There is no known abiotic process, meaning a process without biology, that produces it in significant quantities in planetary atmospheres. The Cambridge team flagged this detection as tentative because the signal sits at the edge of Webb's current sensitivity, but they published it because the scientific community needed to know it was there. A tentative signal from a real instrument aimed at a real planet is not nothing. What this means in practical terms is that astronomers now have a target. They have a planet in a habitable zone at a distance Webb can actually study, showing atmospheric chemistry that includes a molecule with no confirmed non-biological source. The next step is more observation time, additional transits, better signal-to-noise ratios, and confirmation from multiple independent research groups. The James Webb Space Telescope was not designed to be wrong about molecular detections. Its calibration and sensitivity were tested for years before launch. What can change with more data is the confidence level, moving a tentative signal to a confirmed one, or ruling it out entirely. Either answer advances science. The universe apparently builds planets with remarkable variety, and Webb has been systematically surveying that variety since beginning science operations in mid-2022. The TRAPPIST-1 system, a cluster of 7 Earth-sized planets orbiting an M-dwarf star about 39 light-years away, has been one of Webb's primary targets. 3 of those 7 planets orbit in the habitable zone: TRAPPIST-1e, TRAPPIST-1f, and TRAPPIST-1g. Astronomers have known about this system since 2017 and have been waiting for Webb to tell them whether any of those planets have atmospheres worth studying further. The early results from TRAPPIST-1 have been sobering in exactly the way good science sometimes is. TRAPPIST-1b, the innermost planet and not a habitable zone candidate, showed no detectable atmosphere in Webb's first look. TRAPPIST-1c, Slightly farther out, but still inside the habitable zone's inner edge, also showed an atmosphere far thinner than Earth's, or possibly none at all. These results suggest that intense radiation from the host star may have stripped away atmospheric gases from the inner planets over billions of years. M-dwarf stars are long-lived and dim, which makes their habitable zones close in, which exposes planets to high radiation environments. This is the central tension in the search for life around red dwarfs. They are by far the most common type of star in the galaxy, which makes habitable zone planets around them statistically abundant, but the radiation environment may make those planets biologically hostile. This is not a death sentence for life in the TRAPPIST-1 system or in M-dwarf systems generally. Earth's own magnetic field deflects enormous amounts of solar radiation that would otherwise strip our atmosphere away. A planet with a sufficiently strong magnetic field could hold onto its atmosphere even around an active red dwarf. Whether TRAPPIST-1e, F, or G have magnetic fields is something Webb cannot directly measure. That requires detecting certain signatures in a planet's aurora or radio emissions, which falls to future instruments. What Webb can do, and is doing, is narrowing the field, ruling out planets that obviously cannot support life and flagging the ones that might. Beyond the TRAPPIST-1 system, Webb has characterized the atmosphere of WSP-39b, a hot Jupiter, a gas giant orbiting very close to its star, in extraordinary detail. The WSP-39b results, published in a series of papers in Nature in 2022, were not about life. WSP-39b is far too hot for biology, but they were scientifically essential because they proved Webb could do exactly what it was designed to do. The telescope detected sulfur dioxide in WSP-39b's atmosphere, a molecule created by photochemistry, meaning chemical reactions driven by starlight. Nobody had detected photochemical products in an exoplanet atmosphere before with this level of clarity. It confirmed that Webb could read atmospheric chemistry precisely enough to detect trace molecules. That same precision is what makes K2-18b's signals meaningful. The scale of the known exoplanet population is worth pausing on. As of 2024, astronomers have confirmed more than 5,700 exoplanets. The vast majority were found by NASA's Kepler Space Telescope, which operated from 2009 to 2018 and surveyed a fixed patch of sky. Kepler found planets in bulk, but could not study their atmospheres. The TSS mission, the Transiting Exoplanet Survey Satellite, launched in 2018 and still operating, is finding planets closer to Earth, which makes them better targets for Webb's atmospheric follow-up. TESS and Webb are designed, somewhat by luck of timing and somewhat by intent, to work as a pair. TESS finds the candidates, Webb examines them. Within that population of 5,700 plus confirmed planets, astronomers estimate that roughly 1 in 5 Sun-like stars has an Earth-sized planet in the habitable zone. Scale that across the roughly 100 to 400 billion stars in the Milky Way alone, and the number of potentially habitable planets becomes staggering. Hundreds of millions at minimum. Webb will not study hundreds of millions of planets. Its lifetime is estimated at around 20 years given its fuel supply, though the telescope's launch was so precise that it may operate longer. In that time, it can study perhaps a few dozen atmospheres with real depth. The selection of which planets to observe is therefore one of the most consequential decisions in modern astronomy. The criteria scientists use to prioritize targets reflect how much the field has learned. A good Webb target needs to be close enough that the star is bright enough to provide usable signal during transits. The planet needs to transit at all, meaning its orbit is oriented such that it passes in front of its star as seen from Earth. It needs to be in or near the habitable zone. And ideally, its host star should be quiet, meaning low in flares and radiation bursts that would scramble spectroscopic readings. LHS 1140b meets many of these criteria. It orbits a nearby M-dwarf about 49 light-years away, sits in the middle of the habitable zone, and has a density suggesting it may be rocky with a thick atmosphere. Webb observations of LHS 1140b are ongoing, and early results published in 2024 hinted at the possible presence of a nitrogen-rich atmosphere. Not proof of life, but consistent with an atmosphere that could support it. Nitrogen is actually a fascinating detail here. Earth's atmosphere is 78% nitrogen. Nitrogen is chemically boring in the best possible way. It does not react easily, which makes it a stable buffer gas that dilutes oxygen without reacting with it and prevents our atmosphere from being a constant fire hazard. On its own, nitrogen is hard to detect with transmission spectroscopy because it has no strong spectral absorption features in the wavelengths Webb observes. Its presence at LHS 1140b was inferred not from a direct detection, but from the absence of certain other signatures, combined with the planet's bulk density. Inference from absence is a legitimate tool in astronomy, but it requires careful statistical handling, and those results remain preliminary. The question of what harboring life actually means deserves careful treatment, because popular coverage often collapses a very wide spectrum into a single binary. When scientists ask whether a planet could harbor life, they are almost never asking about intelligent civilization. They are asking about microbial life, the kind of life that dominated Earth for the first 3 billion years of its existence. Bacteria, archaea, simple single-celled organisms. These forms of life are extraordinarily durable. They have been found living in hydrothermal vents on the ocean floor where no sunlight reaches. They survive in hypersaline lakes, in acidic hot springs, in the stratosphere, and in solid rock kilometers underground. The term for these organisms is extremophils, life that thrives in extreme conditions. Their existence on Earth fundamentally altered how scientists think about the conditions life requires, because those conditions turned out to be far more flexible than originally assumed. There's a complication in all of this that deserves honest discussion: stellar contamination. When a planet transits its host star, the light filtering through the planet's atmosphere is not the only thing changing. Star spots, regions on the star's surface that are cooler and darker, analogous to sunspots on our own sun, can alter the spectral signature of the starlight in ways that mimic or mask molecular absorption features in the planet's atmosphere. If a star spot happens to be in the path of the transiting planet, or if the out-of-transit brightness of the star is already distorted by spots, the transmission spectrum can be contaminated. This is a real and persistent challenge, and it is particularly acute for M-dwarf stars, which tend to be magnetically active and prone to significant star spot coverage. The atmospheric models used for K2-18b and similar planets must account for stellar contamination, and the research teams do account for it. But it adds uncertainty, and that uncertainty must be propagated honestly through any molecular detection claim. The Cambridge K2-18b team explicitly modeled stellar contamination in their analysis. The DMS signal survived that modeling. That is part of why it was published rather than quietly set aside. Understanding these technical challenges matters because it reframes what confirming a biosignature would actually look like. It would not be a single paper. It would be a sequence, an initial detection, independent reanalysis by a second team using the same data, additional Webb observations producing stronger signal-to-noise, ruling out stellar contamination with dedicated modeling, comparison against photochemical models to exhaust abiotic explanations, and eventually a community-wide consensus statement. That process takes years. The K2-18b DMS tentative detection was published in 2023. If the signal is real, the confirmation timeline probably runs through the late 2020s or early 2030s. Science moves at this speed not because scientists are slow, but because the question is important enough to get right. Ross 508b is another M-dwarf habitable zone candidate discovered in 2022, roughly 37 light-years away. Gliese 12b and Gliese 12c, a pair of nearby candidates announced in 2024, orbit a cool red dwarf just 40 light-years from Earth, with at least one sitting within the habitable zone. Wolf 1069b is a roughly Earth-mass planet in the habitable zone of its star, about 31 light-years away, identified in 2023. The catalog of nearby potentially habitable planets is growing faster than Webb can observe them. Each new entry represents another chance, another system where the chemical toolkit of life might have had time to assemble. The human dimension of this search is not abstract. There are research teams whose entire careers have been aimed at this moment, the moment when a real telescope at sufficient sensitivity could answer the question that every previous generation of scientists could only theorize about. The astronomers who published the K2-18b results were careful in their language, not because they lacked courage, but because the scientific stakes are too high for overclaiming. If a team announces life and turns out to be wrong, the damage to public trust in science is severe and long-lasting. If they are right and they understate it, the finding will be verified and then celebrated appropriately. The incentive structure of rigorous science pushes toward caution, and in this particular case, that caution is the right call. There is also a philosophical dimension that surfaces every time this subject comes up seriously. The Fermi paradox, the observation that if intelligent life is common, we should have heard from it by now, and we haven't, sits in the background of every exoplanet habitability discussion. But the Fermi paradox concerns intelligent, communicating civilizations. Microbial life could be common throughout the galaxy without ever producing radio signals. Detecting chemical biosignatures, the chemical traces life leaves in a planet's atmosphere, is the path to answering whether life is common, long before we could ever know whether intelligence is. Webb is the first tool in human history capable of making progress on that first question. The instruments aboard Webb were built with extraordinary care over decades. The near-infrared spectrograph, known as NIRSPEC, is one of the key tools for atmospheric characterization. It can observe up to 100 objects simultaneously in its multi-object mode. though for transmission spectroscopy of transiting planets, it focuses on a single target at a time. The mid-infrared instrument, or MIRI, covers longer wavelengths and is sensitive to molecules like ozone, a potential biosignature in its own right, because ozone forms from oxygen, and significant atmospheric oxygen is difficult to produce without photosynthesis. MIRI operates at an extraordinarily cold temperature, around 7 Kelvin, which is colder than the background temperature of deep space, and requires an active refrigeration system. It is, in engineering terms, one of the most demanding instruments ever put in orbit. Webb sits at the second Lagrange point known as L2, about 1.5 million kilometers from Earth, in the direction away from the Sun. At L2, the gravitational forces of the Earth and Sun balance in a way that allows the telescope to orbit the Sun in sync with Earth, while staying at that constant distance. This is essential because Webb's heat shield, a 5-layer sun shield the size of a tennis court, needs to keep the telescope permanently pointed away from the Sun, Earth, and Moon simultaneously. Any deviation from that orientation risks warming the detectors. The engineering architecture of the mission was designed around the requirement that this telescope never stop looking at cold, deep space. The operational life of Webb will shape how many of these questions get answered in our lifetimes. If the telescope reaches 20 years of operation, the number of planetary atmospheres it can characterize grows substantially. If it fails early, due to a micrometeorite strike, a mechanical failure, or exhaustion of propellant needed for minor orbit corrections, some questions will remain open until a successor telescope arrives. The proposed LIFE mission, a European Space Agency concept, and NASA's Habitable Worlds Observatory, which is in early planning phases as a large telescope designed specifically for Earth-like planet characterization, represent the next generation. But neither of those missions will fly before the mid-2030s at the earliest. Webb is what we have, and Webb is already making the measurements that matter. Before arriving at that answer, it is worth understanding what atmospheric biosignatures actually are, and why they carry the weight scientists place on them. A biosignature is any measurable property of a planet, chemical, physical, or otherwise, that is difficult to explain without invoking biological processes. The concept is not new. Scientists proposed atmospheric biosignatures decades ago, but they were theoretical constructs because no instrument existed that could actually measure exoplanet atmospheres in detail. Webb made them empirical. When you talk about a biosignature in the context of K2-18b or any other world, you're talking about a measurable signal from a real planet, not a model output. The most discussed atmospheric biosignatures are oxygen, ozone, methane, nitrous oxide, and dimethyl sulfide. Each of these has a known biological source on Earth, and, in most cases, no known abiotic process that produces it in atmospheric concentrations, comparable to what life generates. Oxygen is perhaps the most famous. Earth's atmosphere is 21% oxygen, and that oxygen is overwhelmingly maintained by photosynthesis. Before photosynthetic organisms evolved, roughly 2.7 billion years ago, Earth's atmosphere had almost no free oxygen. The Great Oxidation Event, when oxygen began accumulating in the atmosphere around 2.4 billion years ago, was caused entirely by biological activity. If Webb detected a high concentration of oxygen in an exoplanet atmosphere alongside methane, that combination would be extraordinarily difficult to explain without biology, because the two gases react with each other rapidly. Finding both in abundance means something is producing both continuously. On Earth, the answer to that is life. Nitrous oxide, commonly known as laughing gas, is another biosignature of interest. It is produced by microbial denitrification, the process by which certain bacteria convert nitrates into nitrogen gas as part of the nitrogen cycle. In 2022, researchers at the University of California, Riverside proposed that nitrous oxide may actually be a more reliable biosignature than oxygen in some planetary contexts, because certain abiotic processes can produce oxygen in small amounts under particular stellar radiation environments. But abiotic production of nitrous oxide in detectable atmospheric concentrations is far harder to explain. Webb's sensitivity at the relevant wavelengths makes nitrous oxide a target molecule for future observations of candidate planets. The sensitivity question is central to everything Webb does. The telescope's ability to detect atmospheric molecules depends on how many transits it can observe, how bright the host star is, and how thick the planet's atmosphere is. For K2-18b, the relatively large size of the planet and the comparative dimness of its host star, meaning the planet blocks a larger fraction of starlight during transit, gave Webb enough signal to make tentative molecular detections in just a few transits. For a true Earth analog, a rocky planet roughly Earth's size orbiting a sun-like star at Earth's orbital distance, the geometry is much less favorable. The star is brighter, the planet smaller, the atmospheric signal proportionally weaker. Current estimates suggest that detecting biosignature-level atmospheric chemistry on a true Earth twin around a Sun-like star would require tens to hundreds of transit observations with an instrument significantly more powerful than Webb. That is what the Habitable Worlds Observatory is being designed to accomplish. Webb is the proof of concept. It is demonstrating the technique at its current limits, and those limits are already yielding genuinely extraordinary results. There's also the question of false positives. Scenarios where Webb detects a molecule that looks like a biosignature but has a non-biological explanation. Phosphine became a flashpoint for this problem in 2020 when a team announced its detection in the atmosphere of Venus and suggested it might be a biosignature. The claim was later contested, both on the grounds of the original analysis and on the grounds that abiotic phosphine production in Venusian volcanic conditions might be more plausible than initially assumed. The scientific community spent 2 years working through the methodology before reaching a rough consensus that the initial phosphine detection was likely a calibration artifact or noise. The lesson was not that atmospheric chemistry claims are unreliable. The lesson was that the bar for verification must be extremely high, that independent teams must confirm signals using different data sets, and that every known non-biological explanation must be exhausted before biology is invoked. Webb's results have been subjected to exactly that process for every published claim. The question raised at the start of this video was specific and urgent. Could the planets James Webb is finding harbor life? Here's the honest answer that the data currently supports. K2-18b shows atmospheric chemistry, including a tentatively detected molecule with no known non-biological source in a planetary system where liquid water may exist on or beneath the surface. That is the strongest chemical case for potential habitability, not confirmed habitability, but a chemical environment that is not obviously incompatible with life. TRAPPIST-1's inner planets have been found to be atmospheric poor, raising questions about stellar radiation effects on that system's potentially habitable outer members, which have not yet been fully characterized. LHS 1140b shows possible signs of a nitrogen-rich atmosphere consistent with habitability, though the evidence remains preliminary. LHS 475b, Ross 508b, Gliese 12b, Wolf 1069b. These sit in the queue, waiting for observation time, possibly harboring answers.